All right, we are going to spend this video focusing on combustion analysis questions. I'm going to give you two examples that we're going to work through. One is going to be just a hydrocarbon, so just containing carbon and hydrogen, and then we will get to an example that also involves an oxygenated hydrocarbon that has oxygen present. So what you can see on here is this list here should look really familiar. This is that concept of determining an empirical formula and determining a molecular formula that we've been working on all week. We started with just basic compounds, then we did hydrates, and now we're specifically doing compounds that are undergoing combustion analysis. We are going to follow the same general set of guidelines. We're just going to have to make a few adjustments to adjust for the information that we're starting with. But the more you can connect this to the same process we've been using so far, the better and easier it's going to come to you. So the first step is usually actually the hardest piece of this, determining the starting masses. And this is where this little bit of information is going to hopefully come in handy, at least initially. So this is really dealing with step one. How do we get those masses that we're going to start with? So just remember, in combustion, you're going to have your hydrocarbon, in this case, or in our first example, that's going to be reacting with oxygen gas. I'm leaving out phases just for time right now, to produce CO2 and water. Okay, we did that over the summer assignment. When we go to figure out the moles of carbon in this unknown hydrocarbon, all of that carbon is going to end up as CO2. So we can use the information about CO2 to figure out how much carbon we have. All the hydrogen that is in that hydrocarbon is going to end up as water. Okay, so the mass of the water is always going to help us determine the mass of the hydrogen. Okay, so that's where we're going to start. Then we'll get into how do we deal when there is an oxygen in the unknown compound, or if we have something else like nitrogen, we'll handle in the next video. Okay, all right, so let's get started with this. You have a 1.5 gram sample of a hydrocarbon. So this is my initial mass that I'm dealing with. That's going to be important if we were especially dealing with a compound that involved oxygen. But for right now, it's just some information. It undergoes complete combustion, so all of it reacts. It is going to produce 4.40 grams of CO2 and 2.70 grams of H2O. Okay, what is the empirical formula for this compound? So the CO2 is going to help us get grams of carbon and moles of carbon, and then our H2O is going to help us get our hydrogen. So we're going to just start with the empirical formula. So with this, we have carbon and hydrogen. So I'm going to start with my 4.40 grams of CO2, and it's really important here to label everything because this is usually where students will make a mistake. And then hydrogen is going to be the 2.70 grams of H2O. Okay, remember, we're just interested in the carbon and hydrogen, so we're going to use some dimensional analysis here. So using the molar mass of CO2, we're going to get moles of CO2 that were produced. So 44.01 grams of CO2 per 1 mole of CO2. Okay, we want to get to our moles of just carbon. So this step is important just because I think it helps when we do hydrogen. So 1 mole of CO2 produces 1 mole of carbon, and that's just based on that formula. Okay. When you go and plug this in and you keep it to your 3 sig figs, you should get 0.100 mole of your carbon. Okay. Then we can deal with hydrogen. Water, probably at this point you know, is 18.02 for its molar mass of your H2O. That gives you 1 mole of H2O. And this is where you have to be careful because for every 1 mole of H2O, you get 2 moles, based on that formula in a subscript of 2 moles of hydrogen. Okay, when you go and plug that into your calculator and you keep to the 3 sig figs that you started with, this will end up as 0.300 mole. So this is that point where now we have moles of each element. Okay, from this point on, it's going to be pretty similar to what we've been doing. The only difference here was using the data from the combustion analysis, which was the mass of CO2 to help us get our moles of carbon, and using the mass of H2O to get our moles of hydrogen. Okay, and then from there, it's going to be those same set of steps. We want to find that whole number ratio. So we're going to divide by the 0.1, divide by the 0.1. That will set carbon to 1 in this case. And hydrogen will get set to 3. So carbon and hydrogen is in a 1:3 ratio, which will give us our empirical formula of CH3. So So this is the empirical. Now it did want us to go ahead and figure out what our molecular formula is. We know the molar mass up here is 75. So you would then make sure you're going to take that 75 and I'm going to divide it by the mass of CH3. So 1 carbon, 3 hydrogens. So this is 15.04, which gives me 5. So my molecular formula is 5 times bigger than the empirical. So remember, you're going to multiply all the subscripts by 5. So you get C5H15. And then this is our molecular formula. Okay. So then we're going to move on to our oxygenated hydrocarbon. All right, so the next part is going to follow a similar process, but in this next question, we have oxygen involved. And with oxygen, it adds a little bit of complexity because of the fact that if you think of oxygen being in this compound, we have oxygen that's reacting with oxygen is both the CO2 and H2O, so there's a lot going on here. So how we're going to handle this is we are going to find the carbon and hydrogen first, and I want to find grams of each of those. So let's read through this question. It's talking about we have an organic compound that contains carbon, hydrogen, and oxygen. What's the empirical formula? If you find that the 0.105 is my original unknown, so that's my unknown, and it gives you 0.257 grams of CO2, and 0.0350 grams of H2O when it's completely burned. So we're going to start with carbon and hydrogen here. So carbon, remember, we're always going to get from CO2, so 0.257 grams. Hydrogen, we're going to start with the 0.0350 grams. So initially this is going to be the same set of steps. So I'm going to get carbon using the 44.01 grams of CO2 for every 1 mole of CO2. For every 1 mole of CO2, I get 1 mole of carbon. Now what we're going to do here is I need the mass of carbon that was in this original sample. Because remember, this unknown has carbon, hydrogen, and oxygen. So if I can find the grams of carbon and the grams of hydrogen, I'll know how much oxygen was in that original compound. So we're going to continue this, and I'll show you some variations tomorrow, but this is how I initially like to show students that for every 1 mole of carbon present, that's going to have a mass of 12.01 grams of carbon. So I'm just going right to carbon, grams of carbon. So I have 3 sig figs to start with, so I'm going to take this to 0.0701 grams of carbon. Then I'm going to do the same thing with hydrogen. Okay, and remember this was H2O, sorry, I didn't label those for you. I'm starting with water here, so I'm going to have my 18.02 grams of water for every 1 mole of water. Okay, then I'm going to keep going where my 1 mole of water is equivalent to 2 moles of hydrogen. And then this is where I'm going to go the extra step and show that for every 1 mole of hydrogen, and make sure you actually set this back to 1. Some students will, for some reason, carry that 2 down there. This part just takes care of the fact that every water has 2 hydrogens. This one is just saying that for every mole of hydrogen you have, that would be equivalent to a mass of 1.008 grams of hydrogen. Okay, keeping with the 3 sig figs that we were given, 0.00392 grams of hydrogen. Okay, so that's our grams of carbon, our grams of hydrogen, so the remaining mass of that has to be due to the oxygen. So this is where I'm going to start oxygen. Okay, I originally had my 0.105 grams of the whole compound. Okay, so this has your C, H, and O. Okay, I'm going to then subtract out my grams of carbon. So this is my carbon that I found. I'm then going to subtract out my grams of hydrogen, so that what I have remaining is going to be my grams of oxygen. So let me just slide this up a little bit. When we go to do the subtraction, just keep in mind this is by place value. So because this one is to the thousandth spot, which is less precise than my other 2 values, my grams of oxygen also have to be to that thousandth place. So when I subtract out the carbon and hydrogen, what's left of my unknown is 0.031 grams, and that's of my oxygen. Okay, now I have my grams of carbon, hydrogen, oxygen. This is where the original process takes over. We're going to convert them to moles of each and then find that whole number ratio. So with this, for every 12.01 grams of carbon, I get 1 mole. I'm just going to kind of go through each of these. Hydrogen, 1.008 grams and 1 mole. And then oxygen is going to be 16.00 grams and 1 mole. Okay. Taking carbon to 3 sig figs, I get I know this is going to be tough for you guys to possibly see, so I'll slide that over, 0.00584. Hydrogen is 0.00389 moles. So remember, these are all moles. And then oxygen, just be careful. This will be keeping to the 2.0019. Okay. And then from there, I'm going to divide by the smallest. So this is going to be 0.0019 divided by 0.0019 divided by 0.0019. So here you will see oxygen is set to 1. Hydrogen is going to be rounded off to 2. It's very close to 2. And then the same thing, carbon here is going to be very close to a whole number of 3. Okay, now that I have them in that whole number ratio after dividing by the smallest, I can determine my empirical, which is C3H2O. Okay, if we then, for some reason I don't have this on my paper, if I do my 12.01 times 3 plus 2 times 1.008 plus my 16, okay, we have 108 divided by 54.05. That's going to give me a 2. Okay, and then finally I'm going to multiply all the subscripts by it, so C6H4O2. And that would be my final molecular formula. So again, I would take a second and kind of pause and look through these steps and see how this connects to all the calculations you've been doing, and really take your time looking at the process for this oxygen and make sure it makes sense in the fact that this starting mass is really just we're taking out the carbon that we could find from the CO2, the hydrogen that we could find from the water in order to get that oxygen mass to then complete the calculation. Okay, so we will continue on with this in class shortly. So we'll keep practicing this.